Hi everyone, my name is Mila and today we'll be doing a system design practice exercise. I'm doing this to test out my abilities and hopefully it will help you out as well. Let's dive right into it. Alright, create a worldwide ticketing system where users can purchase tickets. One ticket per user, strictly first come, first serve. Users see a loader until ticket availability is confirmed. 15-minute window for purchase upon availability. Anticipate 1 million users initially, followed by 2 million, then 5 million. Only 50,000 tickets for sale. Sellout time is unknown. Cease request and notify users once sold out. Alright, right away we know that this is going to be a system that's distributed across the globe, so we'll definitely need load balancers. And it says that users see a loader until ticket availability is confirmed. That means that there is consistent communication going back between the client and the user. So we might be using a WebSocket or a long pole. And then let's see, we want to be able to, we're anticipating 1 million users, and that means that we definitely going to need to use cache, as hitting the database with these types of loads is going to be very slow. There are only 50,000 tickets available, and we have to ensure first come, first serve. So that means we have to be very precise in keeping the order of the users as they hit the website to ensure those who arrived first get the opportunity to buy the ticket first. Alright, so let's see here. One thing we definitely want to do is get the global load balancer out of the way. Because this is a worldwide ticketing system, that means we will have our systems distributed across the globe, and we need to be able to determine where those requests should go based on the user's location. Once we get past the global load balancer, what we also want to do is go towards, we want to pass the request to a regional load balancer. And this will further refine the request and send it to a server that is closest and has the lowest latency. Well, that's one way of approaching it. There are many ways to distribute load. There's round robin, low latency, low load, and all of them have their pros and cons. For the sake of our exercise, we'll just use the server with the lowest latency. That simply means that for regions where the population is much higher, we definitely want to make sure that we have more servers and even potentially practice edge serving, which means that we'll have dedicated servers in specific locations like big cities and stuff like that. Alright, so that takes care of that, and then once we get, I've identified the server we want to hit, we're going to direct that request to an API gateway. And this will direct that request to the next appropriate service. Alright, so let's see here. One of the things that I think we can get out of the way right away is cease request and notify users once sold out. So we want to know that if an event has been sold out, to immediately let the users know that there is no more tickets available, and if there are any active connections, kill those requests as well. So send a request back to the client, letting it know to no longer try to connect to the server and see if there are more tickets. To do this, we are going to create an event server event service. And this event service will basically have information about the event. And for that, we can simply have an event data point that says what is the status of the event, whether it's sold out or available, and that will allow us to quickly respond without having to do anything extra. Now, if we look at our DB, we can figure out what our schema should look like. If we take a moment and identify the schema that we will be working with, we definitely will have an event table. That event table will have event ID and status ID. We'll use the status ID to determine if there are tickets available. And then we'll have an event ticket. This will have an event ticket ID and an event ID and status ID. This will help us determine if the ticket has been sold or is still available. And for each one of these, obviously we can have additional data points, but for the sake of this exercise, that's what we will limit it to. Alright, so since we're doing the database schema, let's dive into the rest of it. We will also have a user table, and it will have user ID and other information related to the user that we can utilize for our system. And then we want to also have a user ticket, and this will keep track of all the tickets the user has bought or attempted to buy. So we will have user ticket ID, user ID, and ticket ID. Just gonna move this up here. Additionally, we also know that we're going to have to process payments, and there are multiple ways of approaching this. We could have saved payment information, but for the sake of this, let's just say we don't save that. By not saving any payment information, it allows us to not have to comply to a lot of security and PCI compliance requirements related to sensitive information like that. So we will have user ticket transaction table, which will have the user ticket transaction ID and the user ticket ID. Remember, you can attempt to purchase something and the payment could fail and you can go over it again. Now, we don't necessarily need to save every instances, but for the sake of auditing, I think it's a good idea here to save it. Now, the next question is, what kind of database do we want to utilize? So, because we will be utilizing cache, the type of database we use in for this specific platform, giving it limited scope, we can potentially use MySQL, Postgres, and other relational database. One of the things that is more recent is called NewSQL, which is basically a new version of MySQL that is more geared towards cloud infrastructure and scalability, and has a lot of the benefits that non-SQL databases have. So you will be able to use relationships and scalability while maintaining some of the same SQL syntax. Alright, so here what we're going to do next is we definitely do not want to hit the database constantly, especially if we're getting 10, 20, 30 million requests within a short period of time. For that, what we need to do is utilize a service, a caching service. And what we can use here is Redis. And Redis is an in-memory caching service that allows us to be able to take information from the database, store it in memory, and allow services to access that information with very low latency, allowing us to respond. In addition to that, it also allows us to scale the system as we need to. Alright, so if we look at this flow, what we'll see is the initial request will come in for, let's get the event status. The API will direct that request to the event. It will then see if that information is available in the cache. If it is, it'll pull from there. If it is not, it will hit the database, get that information, and then also populate the cache so that for future requests it doesn't need to hit the database anymore. If the event is sold out, what we're going to do is simply let the client know that it's sold out and it no longer needs to make any requests. However, if the event is still active and there's still tickets available, what we need to do is now create persistent communication between the client and the server. Now, you don't necessarily need persistence, but there are benefits and disadvantages between doing long pulling and WebSockets. For this instance, I think if we just keep it simple and just have a WebSocket service, we can handle not only current requirements but also future requirements. So this will be our WebSocket service. So what will happen is we will hit the event. The event will let us know immediately whether we should continue or if we should immediately send a request back, a response back, letting them know the event is closed. But if it's open, we then open a connection and convert the request from an HTTPS to a WebSocket connection. And then we also will store that information related to the user's connection with the server in the Redis. And the reason we'll do this is at a later point when we need to send communication back to the client, we'll know exactly how to do that by utilizing the information related to that user ID and its connection. Alright, so now that we've established a WebSocket connection, we need to now send that request into a queue. And the best way to utilize this is to use a message broker. And for our instances, we can use either Kafka or Rabbit. I'm familiar with Kafka, so I'm going to go ahead and utilize Kafka here. Now, what's really important here as well is that we want to make sure that we ensure the first come, first serve policy here. And to do that is we got to make sure that each request also has a timestamp associated to it. Now, to do this, we want to make sure that because this is a distributed system, we want to make sure that all the servers across the globe have the same time. And we can utilize that by creating either a network time protocol or a precise time protocol. And I don't think that we might not necessarily need the type of precision what we may, given the simultaneous number of users we will hit. So we'll go with a precise time protocol that our servers will hit independently to make sure that they always have the same timestamp as the rest of the system. And this will keep our clusters all synced up. Alright, so where are we here? So now that we know that the timestamp upon request is precise and synchronized with the rest of the system, we'll send the request with the user information to a Kafka queue. Now, Kafka allows us to sync globally because it has built-in systems designed for global distribution, distributed clusters, and guarantees its order. So this is why Kafka is another good service to utilize here. Finally, what we need to do is subscribe to this Kafka topic where these user messages will be written to. And to do that, we're going to have a ticket ticket service that will be listening to the Kafka topic, and each time it finds that there's a ticket available, it will pull a user from that queue and then process that request. Now, the ticket service will also be listening to Redis. Now, Redis itself has a sub mechanism allowing services and processors to subscribe to these different data points available in Redis, so that if there's a change or new data, it can immediately have access to that information and process it. So the ticket service will be listening to that, and then once it sees that a ticket is available, it'll pull a single user from the queue, and we know that the order is guaranteed, and it will then update the Redis server to say, hey, this ticket is now in the process of being purchased. It will insert a row into the database for that specific user, and then send a request back to the client saying, hey, the user now has that option to purchase the ticket. Alright, and because there's a timestamp, we need to make sure, let's update this to include a timestamp. This timestamp will now be used to determine if the user has attempted to purchase the ticket within the 15-minute window. So the request will go back to the client. The client will then say, hey, I want to purchase this information. So now, as the request comes in, it will no longer go to the API. It will directly go to the WebSocket. The WebSocket will now direct that request to the purchase service, and the purchase service will attempt to process that payment. If that payment is successful, it will update the cache and then also update the database with the user transaction. And if it determines that the user was too late in processing the request, it will then cancel the purchase, update the cache to let the ticket service know the ticket is now available again, and then process that request for the next user. The purchase service will also process the payment information. It can hit a third-party API to do that, and after a successful completion, update that and send back the information to the client saying the purchase was successful. Now, what we need to do also is once the system is aware that all the tickets have been sold out, the events service is also subscribed to Redis. It's always keeping track of how many tickets are available. Once it determines that all the tickets have been sold out, it will send a mass request to all the users, all the connections, letting them know that the tickets are no longer available, and it will also flush the Kafka topic for all the users, and the system will kill all the WebSocket connections. The only other thing is that if the user decides they don't want to purchase the ticket, it will send a cancel request. It will go to the purchase service, letting them know that the purchase has been canceled, and it will update that information, and the ticket service will pick that up again, and the cycle will continue until all the tickets are sold out. So this is a very high level approach. I don't know what I've missed or what I've done wrong. Please leave some feedback, and hopefully you can help me improve, and maybe I can help you improve as well. Thank you so much for your time. Bye everyone.